Hello everyone, this is Ashish.
And this is Isaac.
Today we are going to talk about an interesting electromagnetic appliance, waveguides. So, what is a waveguide? The term waveguide may refer to any linear structure that conveys electromagnetic waves between its endpoints. A waveguide is a structure that guides waves, such as electromagnetic waves or sound, with minimal loss of energy by restricting expansion to one dimension or two. A waveguide confines the wave to propagate in one dimension so that under ideal conditions the wave loses no power while propagating. Due to total reflection at the walls, waves are confined to the interior of a waveguide. We will begin with a rectangular pipe because it is the simplest case to analyze. We will first give a mathematical treatment and come back later to look at the problem in a much more elementary way. Let's first choose some convenient coordinates. We take the z-axis along the length of the pipe and the x and y axis parallel to the sides as shown in the figure. We know that when light waves go down the pipe, they have a transverse electric field. So suppose we look first for solutions in which E is perpendicular to Z, say with only a y component, Ey. This electric field will have some variation across the guide. In fact, it must go to zero at the sides parallel to the y-axis because the currents and charges in a conductor always adjust themselves so that there is no tangential component of the electric field at the surface of the conductor. So Ey will vary with x in some arc as shown. Since we want the waves that propagate down the guide, we expect the field to alternate between positive and negative values as we go along in z, and these oscillations will travel along the guide with some velocity v. If we have oscillations at some definite frequency omega, we would guess that the wave might vary with z like cos omega t minus kz, or to use the more convenient mathematical form like e power I omega t minus kz. This z dependence represents a wave traveling with the speed v equal to omega by kz. So, we might guess that the wave in the guide would have the following mathematical form. Electric field should have no tangential components at the conductors. Electric field should be perpendicular to the top and bottom faces and to be zero at the two sides faces. First condition is already satisfied by our filed equation. Second equation will be satisfied if we choose kx such that kx into a is a multiple of pi. Therefore, kx into a equal to pi, where a is the width of the inside of the guide. Divergence of E must be 0 in the free space inside the guide since there are no charges there. Our E has only a y component and it doesn't change with y, so we do have that del dot E equal to 0. Electric field must agree with the rest of Maxwell equations in the free space inside the guide. The second derivative of Ey with respect to x is just minus k square x Ey. The second derivative with respect to y is 0 since nothing depends on y. The second derivative with respect to z is minus kz square Ey. And the second derivative with respect to time is minus omega square Ey.
The above equation implies kx square plus kz square minus omega square by c square into Ey is 0. Unless Ey is 0, this equation further simplifies to kx square plus kz square minus omega square by c square equal to 0. And substituting kx equal to pi by a in this equation, we get a nice equation for kz, that's root over omega square by c square minus pi square by a square. Now this expression of kz shows that as we go into higher and higher frequencies, the wave number kz becomes omega by c. But if we go towards lower frequencies, the kz becomes imaginary for a certain value of omega. Here, the cutoff frequency or critical frequency comes into play. The cutoff frequency is the frequency at which kz is 0. So the cutoff frequency is given by omega c is pi c by a. When frequency becomes lower than omega c, the wave number kz will be kz is plus or minus ik bar, where k bar is a positive real number. Then the field equation eventually becomes Ey is E naught e power plus or minus k bar e power I omega t sin kxx. The sign that goes with KR must be the one that makes the field decrease with increasing distance from the source of wave. So, for frequencies below omega c's pi c by A, waves do not propagate down the guide. The oscillating fields penetrate into the guide only a distance of the order of 1 by k bar, as shown by the graph. For this reason, the frequency omega c is called cutoff frequency of the guide. Now we know that the phase velocity is given by omega by kz. That's c by root over 1 minus omega c by omega whole square. For frequencies above cutoff, where traveling waves exist and omega c by omega whole square is less than 1, the phase velocity is real and greater than c. This is possible because it is just the nodes of wave that are moving and not the energy or information. To know how fast signals will travel, we have to calculate the speed of pulses or modulations made by the interference of a wave of one frequency with one or more waves or slightly different frequencies. This speed is called as group velocity. The group velocity is given by d omega by dk. That's in our case c into root over 1 minus omega c by omega whole square, which is less than speed of light. This is curious to observe that the geometric mean of V phase and V group is just C. What are the uses of waveguides? Now we have learned what are the waveguides and the theory behind them. So these appliances are used in transmission or reception if the electromagnetic waves we are interested are in the frequencies of order of microwaves. It's mostly used in airborne radar. The waveguides are used with cavity resonators to carry input and output signals. Waveguides are also used in devices of navigation aids. References: Feynman's lectures and day notes on waveguide construction. Thank you. This presentation was presented by Ashish and Isaac.